Okay, this video is for AP Calculus, and we're talking about volumes of solids of revolution using what's called the disk method, or its extension called the washer method. So we established in the previous video that integrals are summation machines. They can sum things together, right? And so far, what we've done is find an area under a curve, or in the case where we have two curves, an area between curves, where we have a little width here, which is in this case in dx. It's in the x direction, if that's the x-axis. Right? And then we have a distance here, which is height. And if you take that height and you multiply by that width, you get a two-dimensional area, right? So the height times the width gives us an area. The height is the height of the function f of x, and the width is a little change. It's an infinitesimally small change, in this case in the x direction. So that f of x times dx represents an area, and then we're summing all those from x equals a to x equals b to find the two-dimensional area that's between this function curve and the x-axis. Okay, but what if we wanted to find the volume of a three-dimensional object? Now, in general, we can't do this for just arbitrary shapes, at least not in this calculus class. In the next calculus class, Calculus 3, where we move up into 3 dimensions, we do have some techniques that will allow us to integrate in multiple directions, and really kind of a powerful and interesting thing. But in the class we have now, we're just going to integrate along a single axis. And there is a certain set of objects that we can find the volumes of if they have certain kind of symmetry, a rotational symmetry. Right? So have you ever seen these holiday decorations that are made out of tissue paper, and they start out with a shape like this, but then they kind of rotate around an axis into kind of a three-dimensional shape like an accordion style? Right? That is what we call a volume of solid of revolution. We have an axis of rotation that we're rotating around, but it's that same exact two-dimensional shape, just replicated at all the different angles all the way around there. Right? So this is called a volume of solid of revolution, because we take an area and revolve it to form the volume. So in that case, right, what you can do is you can cover that shape, that volume, in two ways. Right? This animation kind of shows this. You can take the area and rotate it, and that would produce that volume if we summed up all the slices. But you can also take slices the other way through this. And those slices, see, those slices are little circles. Right? They're little, it's like summing up a whole bunch of slices of circles to fill that same volume. Well, we're going to have those circles have a specific disk. So if you imagine you pause this and took one circle out of here like this, but instead you gave it a little infinite width here, like a little change in the x direction, let's say, right? Then you could find the cross-sectional area of this, right, which is a circle. Right? That area is a circle, pi r squared, and then there's a little distance here. Maybe we could call this distance here r for the radius, and then this, maybe we just use delta h for height, because it's a little height. Then that circle, if it's actually got a thickness to it, is what we call a cylinder or a disk. In geometry, we call the shape a cylinder, and in calculus, we call this a disk. It can either be spelled D-I-S-C or D-I-S-K. And so what is the volume inside that little disk? Well, any shape which has an area that's extruded in the other direction is the area that's enclosed by one of the dimensions here, in this case pi r squared, and then it's just this area replicated if this is delta h times. So we're going to come up with an equation for the volume there. Right? Let me just jump up to that. Right? It is that pi r squared area times that change in h, and that gives me the volume in that thin cylinder. Right? Now, of course, we don't want to just do a really chunky cylinder and just stick a bunch of cylinders like this in here. Right? We want to take the limit as the number of cylinders approaches infinity, so that this fills this whole area with a very smooth volume that is really close to the actual volume. And that's why we're going to sum an infinitely thin. These are going to be like a dx or a dy, an infinitely thin dimension, a paper thin cylinder, something like that. So we can very closely match that. And that means that the volume is going to be a summation of volumes of these little cylinder volumes. But each of these are pi r squared times the little height. That height is a little change And so this is either going to become from A to B pi r squared, and then this is going to be a dx, or in some cases that might be a dy, and it will change along one of the axes. All right. So to find this, if we are doing something where we have an axis of rotation which is around, so that we have a two-dimensional area here that's being rotated around the x-axis, then that means that we're going to be putting our rectangle perpendicular to that axis of rotation. So I'm going to introduce a phrase that will help you keep that in mind. When you're doing the disk method, right, the rectangle is perpendicular to the axis of rotation. I know it's corny, but it does help us to remember that the rectangle has to be drawn in a direction that's perpendicular to the axis of rotation. It also must grow from the axis of rotation. And the reason why that's true is because when we have that rectangle and we rotate that rectangle around the axis of rotation, that's going to make the cylinder shape, the disk, and this dimension must be a radius. Let me change colors here so this shows up better. This dimension must be a radius, right? And therefore, since radiuses always grow from the point of rotation, this rectangle has to start where the rotation is around. It has to start at the axis of rotation. All right, so we're going to have the formula. What I'd like for you to memorize is this. The volume for disk method is an integral from a to b of pi r squared times a little change in height. Okay, as compared to the area between curves was an area of a height times a little change in width. Right. So now we have, this was a one dimension times one dimension to give me a two-dimensional area. This is a two-dimensional area times a one-dimensional distance to give me a three-dimensional volume. Right, so this is the formula we're going to work with here. The integral for the volume is an integral from a to b of pi r squared times a little change in the integration axis. All right, now that could be that we're rotating around the y-axis. If we're taking a two-dimensional area like this area over here, and we're rotating it around the y-axis, and that means that the rectangle is going to grow perpendicular to that, and it's going to rotate around. The radius will be in the x direction, and we'll be summing in the y direction. So this delta h could be either dy or dx. But whatever we establish here, if this is, say, a y, then that means these are starting and stopping y values, and that means this function can contain only the variable y in here. So everything is either x or y. So that suggests a procedure we could use to find the volume of a solid revolution. We're always going to start by drawing a sketch, show that 3D rotation into a solid. We're selecting our method here, which is disk, and then we'll draw the rectangle. The rectangle is perpendicular to the axis of rotation, perpendicular. And we determine if that little width is a dx or a dy, because that establishes the integration variable. And then imagine that we rotate the rectangle around to make the cylinder shape. Figure out what r is, and then insert that in here. Figure out the correct boundaries, and then integrate. All right, let's just take a look at a few. As always, you can pause the video and try these on your own if you would like. So find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. We have y equals x squared. And let me just graph each of these in turn. Y equals x squared. I'm going to put some tick marks on here. Y equals x squared would go through the point 1, 1, and 2, 4. So something about this wide. Y equals x squared, like that. The y-axis, y equals 4, which is a horizontal line, in the first quadrant. So we have to identify the two-dimensional region. That's the region we're talking about. We're rotating around the y-axis. So I'm going to change colors here and mark that we're rotating around the y-axis. Right? So that means if you imagine rotating this around there, you're going to get a shape. So kind of a half of a football shape of volume in front of you. Okay, then we're going to put the rectangle on here. Perpendicular means if this is the axis of rotation, the rectangle has to be drawn in perpendicular to that. So we're going to go somewhere in the middle of the bulk here. Starting at the axis of rotation, we'll have a rectangle grow until it fills up all of the space in there. And this is completely full. And this little width is in the y direction, so that's dy. Okay. That also means that we can label the radius. So imagine if we rotated this around, that would make a little cylinder shape. And the radius of that shape is this right here. That's the r, because that has to go from the axis of rotation out to the edge of the rectangle. So now I'm going to have to come up with an equation for that. Okay? So the bottom of this is 0, but the top of this is an x value, because this is moving in the x direction. So this curve is y equals x squared, but I'm going to have to solve this for y, or sorry, for x. So that means x is plus or minus the square root of y. And this is a place where x is positive, so it's x is the square root of y. And that means this radius is the square root of y. And so I'm thinking of this is a movement in the x direction, or a distance in the x direction. So this m is going to be an x value, and it's x equals the square root of y. Therefore, this r is equal to the square root of y. Now we can set up our volume. The volume is an integral from a to b of pi r squared dh, right? And in this case, it's pi, the radius is the square root of y squared, and the little rectangles in the y direction. Sanity check, if that's a y, this function can only contain y's, that's perfect. And that means these boundaries have to be y values. So if this is the point 0, 0, let's see, this up here would be the line y equals 4. That means we have to go from y equals 0 to y equals 4. And then we could either integrate that by hand, or we could use math 9. Use math 9, you get 25.133. No units are provided. If there were units, like if these were in inches, this would be cubic inches because it's a three-dimensional. All right, and that's it. That's how disk method volumes work. And there's a lot of stuff going on there. Start with a sketch. Figure out what region is being included. Picture the axis of rotation and how this produces a shape. Once you've identified the axis of rotation, put a rectangle that grows perpendicular, so perpendicular to the axis of rotation, starts at the axis of rotation grows until the material is covered. If you imagine rotating that around, you can picture where the radius is. Figure out whether this is dx or dy. Figure out an equation for r in terms of that variable, and then plug into the form pi r squared dh. Establish the boundaries and integrate. Okay, let's take a look at this next one. This next one says, same setup, except we're going to rotate around the x-axis. So let me repeat the graph here. All right, so we've got that same setup here. We've got y equals 4. Got the parabola in the first quadrant here, that's this. But this time, we're rotating around the x-axis. So if we're rotating around the x-axis, that means the other shape would be over here. We would have a shape that looks like this, kind of like a hockey puck with a bunch of material cut out of the middle. Okay? All right, so we will put our rectangle on here. If we try to do it this way, we would put our rectangle on here. It's got to be perpendicular to the axis of rotation. So now the axis of rotation is here. And that means since my rectangle has to grow from the axis of rotation, I'm just going to go somewhere in the middle of the bulk here. I'll draw my rectangle in here until I have no more material. But now I have to go through a hole for a while before I get to material. All right, so how do we handle that? How do we handle a case where we have to go through some space before we get to stuff, right? Well, the way we're going to handle that is to use two integrals, similar to the top minus bottom case when we did area between the curves. This is sometimes referred to as the washer method, but It's just the disk method with a hole in the middle, right? So if we have that shape there, imagine if you rotated it out, you would get this hockey puck with the middle here. But that means that if you rotate the portion of this rectangle that has the shape, right, it's going to form something that looks more like a washer, right? It's going to have a top end that's rotated around, but it's going to have a bottom end that rotates around too. So that's why sometimes this is called the washer method, right? But the way we're going to do that is we're going to first establish, I'm going to call this R. I like to label this R, so there's going to be I like to use a capital R for the longer radius and a small r for the smaller radius. So the capital R is the radius of the entire rectangle, right? And if you were to just find pi capital R squared times, in this case, the x, or this would give you the entire hockey puck, right? Then we'll subtract out the piece in the middle, the hole, by using pi little r, the radius of the hole, to get the volume in between the two, which is the volume of the washer. Okay, so you can think of it as, a capital R. I like to use capital R, lowercase r. The capital R is the edge of the material, and the lowercase r is the edge of the hole. And you're subtracting the two. Okay, I think it's actually safest to do this with two different integrals, and we'll see why in a second. And then just do another integral for this. So let's rework this problem. It suggests that we can add an additional step to our procedure. Determine if the rectangle is completely filled. We're going to use the washer method with two integrals of a capital R squared minus an R squared if we have a hole. Procedure is basically the same. So here's what I would do. I would start with the sketch. So we get back to where we were. We have the y equals 4. We have the parabola. Y equals the square root of x. This was the region. We're rotating it around the x-axis. So this is the axis of rotation, rotating around the x-axis to form this shape here. This is the rest of it, and it would kind of look like that. Okay, we're going to put our rectangle in, which has to grow from the axis of rotation and until it covers material. Since we go through a hole first, that means we've got two radiuses, and we mark both of them on here. Okay, this radius here, we're going to label capital R, and this radius here, we're going to label lowercase r. So the capital R, right, is established by this boundary, and that boundary is just 4, right? So this is just in the y direction, it's just y equals 4, so the radius is always 4. Right? The lowercase r is established by this boundary, and it's how far up this is in y. So since that y is x squared, that means this radius is x squared. So now I've got a radius to the edge of the rectangle, a radius to the edge of the hole, and now I can say, oh, I've got the washer case, so I've got two integrals. An integral from a to b of pi big R squared dh minus pi little r squared dh. We know that this rectangle is in the x direction, like that little opening. So that means this volume is going to be an integral of pi. Now this radius here is x squared, so that will be squared, and then this is dx. And then this is pi, and this little radius is, oh, I'm sorry, I made a mistake here. The big R is 4. So the big R is 4, always being squared dx. The little r is the one that is x squared, and then that's squared because of pi r squared dx. And then we have to cover this in the x direction. So this definitely starts at x is 0. This ends when we get here. So to figure out this coordinate, what I'm going to do is intersect these two objects. We have y equals 4 and y equals x squared. Anytime I have an intersection, if you think of it as a system, x squared would have to equal 4. So x is either 2 or negative 2. So this is the point when x is 2, y would be 4. So that means we're going to stop when we get to 2. So the correct boundaries would be 0 to 2, because we can't use 0 and 4 anymore. Those are y values. This is an x type integral, so that would be x values. Right, and that turns out to be, if you do math 9 here, turns out to be 80.425. Okay, so that's the setup to do that example. Okay, we're just going to see other cases, and there's one other twist that we'll sometimes have in Calc BC that you might not have seen in AP Calc AV if you took an AP Calc AC course last year. This twist right here. What if we don't rotate about an axis? What if we rotate about some other horizontal or vertical line? So let's graph this situation. We've got the same setup except for the axis of rotation. So let's try to make this more precise. Okay, so I've got y equals 4. It's this line, y equals 4. But I also have this line, y equals -2. This is the axis of rotation. We have the parabola, y equals x squared, and this is the area. This time, we're rotating around this line here. This is the axis of rotation. Okay, so the rules are the same. We still have a rectangle that grows perpendicular from the axis of rotation. So it's going to start, and it's going to start down here. Go through a hole for a while before it gets to the material. Some of this is filled in and some is whole. And this is a dx type rectangle. So we'll have dx there. Okay, let's put some boundaries here to show what the big radius would be. That would be the big radius. And the little radius would be there. Okay. Now hopefully you agree that the big radius is, this is always 4. This is always 4. And this distance is always 2, so the big radius is always 6. Agree with that? There's an offset, and we just add that to this. Okay, for the r, what I'm going to do is, this particular rectangle's r is right here, right? And what this is the y value for the rectangle, which is x squared. So this distance right here is x squared, right? But this distance is always 2, right? And the r goes all the way from here to here. So every one of these you kind of have to sketch to see what's going on. But this is x, we have this x squared distance, we have to add 2 to that to get the little r. So it's x squared plus 2 in this case. Right, but the rest of the setup is exactly the same. So the volume is going to be a washer type. So it's going to be from A to B of a pi big R squared dh minus a little pi little r squared dh. Right, so that's going to be, well, let's see. We're doing a dx type. So this is pi. The big R is always 6 in this case, dx. And then this will be a pi little r, which is x squared plus 2 big squared dx. And then since this is an x, we're going again from x is 0, and that intersection was 2 from before. So this is also from 0 to 2, 0 to 2. This would be the setup. To give you the answer, now this volume should be larger because although we have the same area and it's rotating through a larger period of larger amount of space. So it's sweeping actually out more volume. And so it's not surprising to me that this answer is larger, 147.455, than when we rotated around a smaller radius. Okay. So that's the basic idea. I think we will, I'm going to split the other, I have 3 more examples, but I'm going to split them off into a separate video. So if you feel you have this already, you're good to go, you can jump in. But if you want more examples of situations here with offset axes or with whole cases, we'll cover them in a second extension video.